about talking about the history of radioactivity. So we talked about the difference between fission and fusion. And so if we look at something like fission on here, then we'll see if this... Here is a neutron, and the neutron's hitting into the nucleus, and then you can see the two fission fragments. The problem is that in addition to that fragmenting off, what else is being given off here? What are these right here representing? Those are the neutrons that end up coming off. And so in fission, it's breaking apart, and those two are breaking apart from each other. So let's come back here, and then we have fusion. And on fusion, what ends up happening? What happens with fusion?
They combine.
Yeah, now instead, they're going to combine, and they're going to come together. And so, let me restart this. And play. Okay, so this is showing tritium, and then deuterium is right there. So deuterium being 2 and tritium being 3, and then you have the fusion. And then the 2 split off again, that's representing a neutron, and what ends up being left behind is helium. What we're going to talk about right now is what those particles are, and they're different types of particles that are given off during radioactive decay. They're what are called alpha particles, beta particles, gamma, there's positron emission, there's something called electron capture. So we're going to talk about these different things, these different modes today. If you take a look at your periodic table, let's take a look at the periodic table for just a minute here. And I'm going to have someone, actually I can just read this real quick in a second here. You can see that there's this table of radioactive isotopes. And what do you think these numbers here, well we'll talk about these numbers right here, but it says H with the 1, BE with the 4, C with the 6, F with the 9. What's that number representing down there? Atomic number, perfect. Those atomic numbers are the same that they are at the big blue number on the periodic table. So that's representing the atomic number. So then what do you think this number is representing? If it says like F18 or 14 or 11, that then is the mass. The mass is not just equal to the number of protons. The mass is equal to protons and neutrons. Why not electrons?
Because they don't weigh.
Perfect. Their mass is insignificant in comparison to the other two. So those are not included. So this is showing the mass. Then it says 15.3 min, 12.26 Y, there's a D, there's another Y, a min, a Y, a min. What do you think those are representing?
Time.
And there's an H? Good, time. Those are hours, days, minutes, years. And then there's this symbol that basically comes after it, okay? And so I'm going to read this for you real quick here too. Let's see if I can get right in the middle of it so we can see it. So it says selected radioactive isotopes. Naturally occurring radioactive isotopes are designated by a mass number in blue, although some are also manufactured. Letter M indicates an isomer of another isotope of the same mass number. Half-lives follow in parentheses, where S, min, H, G, and Y stand for seconds, minutes, hours, days, and years, like we said. The table includes mainly the longer-lived radioactive isotopes. Many others have been prepared. Isotopes known to be radioactive but with half-lives exceeding 10 to 12 years have not been included. Symbols describing the principal mode or modes of decay are as follows. There is what is called alpha emission, there's beta, and we're going to talk about these today. Positron, what is called EC, electron capture. IT, isomeric transition, and then SF, which is called spontaneous fission. Now the only thing that's really important is it says that these are typically accompanied by gamma. Gamma is not being shown on any of these, so if you look at these, it'll either say alpha, beta, gamma, or this EC, or this beta plus, which is called positron emission. But they don't actually show gamma. And the idea is that gamma would be accompanying these in addition. They're just not showing it every single time. So let's come back to, what do you think this number means? This 37.2 min, or the 165 days. What do you think that represents? Yes?
The time it takes to start the radioactive decay.
Time it takes to start decay.
The half-life?
The half-life. It is representing the half-life. And the half-life, everybody, you can say it, is the time it takes for how much of it? Half of it to do what?
Decay.
To decay. And that's where the decay piece comes in. Perfect. So it's the time it takes for half of it to decay. So that means if you're starting with 100 grams of something, after one half-life, how much do you have? 50, half. And after another half-life, how much do you have? If you have 50 now, you have 25. A misconception is, I have 100, Now after one half-life, I have 50 grams, and after another half-life, I lose another 50 grams and I have 0.
No.
That's not true. It keeps splitting in half every single time. So the idea would be that in theory, you would never actually get to what? 0. You keep on splitting it in half, in half, in half, in half again. And so that would be the idea of how half-life works. So really important that you understand this. Later on, what we'll do is we'll do calculations with this. But to start, we're just going to talk about the different modes of decay. Okay, so let's take a look back at the notes here. So now we're flipping to the second page here. So nuclear cadmium, what is called the belt of stability. Most elements have different isotopes. And an isotope, if you remember from the beginning of the year, we call them isotope, isoprotes. So these have the same number of what? Protons. Meaning their identity is the same, okay, but they have a different number of what in the nucleus? Neutrons. Good. Remember, if they have a different number of electrons, those are called ions, not isotopes. Those are charged particles. So now we're just talking about the nucleus. Therefore, they're the same element, but with a different what? Mass. Oh, you guys rock. Okay. For stable isotopes, an interesting plot arises when the number of neutrons is plotted versus the number of protons. This is neutron versus proton, okay? So you always say Y versus X. Neutron versus proton is what this is showing, not mass. So this number up here is not the mass. If this is representing the number of protons, then that's also called, the number of protons are called the atomic number. So in other words, we don't have an atomic number 0. Where does this start? 1, with hydrogen, right? So if I looked at something like element number 60, what would element number 60 be? So if you find on the periodic table, what's element number 60?
ND.
This ND. Neodymium. Yeah. So then that would be that particular element, and then it has the number of neutrons. Okay? So we're going to come back to this in just a minute. Because the plot shows only stable isotopes, this graph is often called the, and you might be able to find it somewhere. Everybody, I heard you say it. Belt of stability. Nice. It is called the belt of stability. And next week, I'll talk to you about the schedule, by the way, for next week. But there's going to be a quiz on this stuff. Make sure you know what this is called, okay? So the belt of stability. The plot indicates that lighter isotopes are most stable when the neutron to proton ratio is 1 to 1. I want you to take a look at this. The first thing is, this line, this straight line, is not the belt of stability, okay? What this is showing is this line here is showing a 1 to 1 ratio of neutrons to protons. Oops, that's what that line is showing right there. Okay, so that line is not showing, oh, it disappeared. Oops. Undo. Okay, so that one's showing a 1 to 1 neutron to proton ratio. This here is what our belt of stability is. It's this red line right here. So this part right here is our belt. Okay, that's the part that's the belt. Where, between what elements, what number of protons, does the linear 1 to 1 ratio match up with the belt of stability? Between what elements does this linear plot basically line up? Between what elements? What number elements? What atomic numbers? 1 to 20. Perfect. Between 1 and 20 is basically where your belt of stability pretty much hits on that linear 1 to 1 ratio. But if you look at something like element 60 and you come straight up from element 60 and we try to hit the belt, where does the belt hit? How many neutrons do you have? Something like 80. Okay? So now it's changed. It's no longer a 1 to 1 ratio. So this line is just showing where the 1 to 1 is, and then that's supposed to be called the belt of stability. What happens is elements that are radioactive will decay until they reach the belt. Okay? So if an element is out here, what will happen is it will end up decaying, and sometimes it's a huge process, and it goes through maybe 10 steps, sometimes it's 20 steps before it actually reaches the belt. And it goes through different modes of decay until it finally stops there, okay? And then you would call it, instead of saying that it's radioactive, you would call it a what isotope, saying that it's pretty much going to stay the same. We call that
Stable.
Stable. Perfect. Then you would call it a stable isotope, okay? So it says the neutron to proton ratio is 1 to 1 for the lighter isotopes. This is the case with any nucleus that has up to 20 protons. As the atomic number increases beyond 20, It appears that a stable nucleus is able to accommodate more neutrons. The neutron to proton ratio rises, so now it's closer to 1.5 to 1 for the stable isotopes between 20 and 83. What do you notice after element number 83? What happens after element 83?
Farther apart.
They're no longer what?
Radioactive. Stable.
No longer stable, right? Now they're all radioactive, right? So now they are all radioactive, and then they have to decay in order to reach the belt of stability. Elements past number 83 are all radioactive. Okay. What do we call this thing again? The what?
The belt
of stability. The belt of stability.
We have to graph that.
Stability. No, but you need to know that it's called the belt of stability. And you also need to know that between 1 and 20 is where it's a 1-to-1 ratio, and that anything past 83 is going to be radioactive. So the typical modes of radioactive decay are called alpha, beta, gamma, and positron. There's also electron capture. I'll tell you why later, why we're not going to study electron capture today, but it is one of the modes. The atoms will decay until they reach a more stable isotope, one that falls on the belt of stability. So the stable isotope is what they're trying to get. Okay? First one is called alpha. What alpha looks like is, we're going to draw it again. I know it's drawn right there for you, but just so that you get used to it. It looks like, kind of like a fish symbol. So everybody draw this fish symbol. And when it comes off, it looks like a helium nucleus coming off. And so what it basically looks like, how many protons does helium have? 2. And then if it's 2 protons, then if it's a stable nucleus, it's probably going to have how many neutrons? 2. So that gives us a total of what mass? 4. Because remember, in your nucleus, you have protons and neutrons. Okay? So that would be a 4-2. It can also be written as 4-2 helium. But it doesn't, typically they don't have it with electrons going around it, so it's just a helium nucleus that's being released without electrons. Okay? During alpha decay, a helium nucleus is released. What we're going to do is we're going to redo this. So let's, even though it's there, I wanted it to be there, I want to show you what it would look like on paper, what it would look like for you. Okay? It would say something like uranium-238 going through alpha decay. And then you would have to write it all out. Okay? So we know that this top number represents the mass. And what does the bottom number represent? The number of protons. So the number that comes after the dash is actually your mass number. Okay, that's the number that goes on top. So if it were going through alpha decay, what you would do is you would first write what an alpha particle looks like. And an alpha particle is going to be this fish symbol. What's the top number? What's the mass of an alpha particle?
4.
4. And it's always going to be the same, so you'll end up memorizing this. How many protons does it have? 2. Plus. We just finished studying and doing the lab on the law of conservation of mass. Now we're talking about mass and matter. That the amount of mass or matter that you have on your reactant side must be what? Equal to the amount of mass on your product side. It's not just one of them, it's in total. Okay? So the case of the matter here is that I've got 238 as my mass, my total protons and neutrons. 4 of them come off, so the question is, how many are left over?
234.
234. That's your top number of the particle that's going to be your next particle after it decays. What element has it turned into? If this is 92 and we're accounting for 2 in the alpha particle, how many are left over here? 90. Now the question is, how am I supposed to figure out what element it is? Periodic table. 90 is the blue number. Take a look. What is it? TH, thorium. Nice. Okay? So this you're going to write as thorium, TH. And that's how they get this answer here. Alpha particles are pretty big. You can take a piece of paper and stop the alpha particles, so just with a piece of paper. So if alpha particles were being shot, they would not pass through something like a piece of paper. Okay? So stopped by paper. They're, in regards to, in talking about different modes of radiation, these are the biggest types of particles that are being emitted. Okay. The mass number, what happened to the mass number of the nuclide? When they say nuclide, they're talking about the actual nucleus of the element. So what happened to the mass number? It decreased by how much? By how many? By 4. And what about your number of protons? What happened to the number of protons? That decreased by 2. Good. decreases by 2. As an alpha particle is emitted, the number of neutrons and the protons decreases, and it creates a more stable type of atom. Next one's beta. Beta we're going to draw again. It's like a letter B, but with a hook. So I kind of draw a long hook, and then I do my B. Okay, so this one's interesting. What happens with beta decay is a neutron turns into a proton in the nucleus. And when the neutron turns into the proton, it actually gives off what appears to be an electron. But are there electrons in the nucleus? No. But the particle looks just like an electron. What mass, remember the top number is the mass, what mass does an electron have?
0.
0. How many protons does an electron have?
-1.
-1. Nice. This is called the beta particle. Sometimes they'll write it as beta minus. Typically it's just written as beta that way, as a negative charge. There is what is called the positron we'll talk about in 1 second here. This is also written as an electron because of that. Okay, you can also write it as an electron. So this can be written either as alpha or helium. Either one you'll get points for. This one can be written as beta or an electron. During beta emission, what happens is a neutron turns into a proton, and a beta particle or an electron ends up increasing your atomic number by 1. So let's try this again. Let's cross off what this says. This would say something like C14 going through beta decay. That's what it would say. Okay, it would say, show a reaction for carbon-14 going through beta decay. So again, carbon-14, we know that it has 6 protons, and we have our arrow. What's the beta particle look like? Let's just do it as a beta particle. The mass again is 0, and the number of protons? -1, plus. If the top number is 14, and that's a 0, what are you left over with? 14. The mass doesn't change. Why doesn't the mass change? Because electrons are weightless, that's what it's giving off, is basically like emitting an electron, but something's changing. You're losing a neutron. So if you're losing a neutron, why isn't your mass changing? Perfect. And what do you know about the mass of the neutron in comparison to the proton?
Same.
They're basically the same. Perfect. Okay, they're basically the same, so that's not going to change. Now let's look at the bottom number. Careful with this. It's 6 here. It gives off a -1, so what must this number be?
7.
7. Nice. Not 5, but 7. So 7 plus -1 is equal to 6. So these sides, the bottom numbers have to be equal, and then the top numbers have to be equal on either side of the arrow. So then you look on the periodic table, what's atomic number 7? Nitrogen. Perfect. So that's what it's decaying into. So carbon-14 dating that's a method of dating that they use. And the idea, actually we'll talk about it a little bit later, but the paper, it basically looks like has disintegrated. And the idea is that instead of having carbon, the solid carbon, it actually turns into nitrogen as like a gas, okay? And so that it ends up escaping. These can be stopped by a piece of wood. So if you have a piece of wood, piece of paper will not stop beta particles, but a piece of wood will stop beta particles. So something as dense as wood would end up stopping the beta particles. This one's really fast. Oh, the net effect is that a neutron becomes a proton. We talked about that by ejecting an electron. The result of beta decay is that the mass stays the same. But the number of neutrons, what happened to the number of neutrons? Decreases by 1. While the number of protons increases by 1. And so then they end up canceling each other out, basically. So your neutron to proton ratio decreases. Again, that gets closer to the belt of stability. Positron emission, again, let's do this B. How is this different? Well, it still has no mass, but instead of being, it's like having a positive electron, which means the charge down here would be what? +1. It's not like a proton. Why is it more like an electron than it is like a proton? Yes?
Mass is the same.
Perfect, because the mass is 0, basically. Okay, if the mass were 1, then you would say that that would be identical to a proton, but it's not. Okay. So positrons have the same mass as an electron, but a positive 1 charge. When a positron is emitted, a proton turns into a neutron. Really easy to remember. You know how I always do the play on words or the letters or whatever? Positron starts with what changing? What is disintegrating?
Proton.
The proton, P and P. Okay? So in beta decay, it's a neutron turning into a proton. This starts with a P, so it's a proton turning into a neutron. So maybe on a multiple choice question, you would be asked something like this, like in positron emission or in beta emission, what's happening? Is it an electron turning into a proton? Is it a proton disintegrating into an electron? What's happening? So just remembering that is going to be an important piece. Same thing here. So doing another one of these. So let's cross this off again. Let's just start it all over and say carbon 11 going through positron emission. Okay, and let's try this one. Okay, so what we would do is we would write C11, and then what number goes on the bottom for carbon? Always 6. Remember, that never changes. That's the identity of the atom. Arrow. Okay, so beta plus. We're going to do our beta plus, which is what number on top? 0. What number on the bottom?
1.
Plus 1. Perfect. Plus. Now we need to figure out what we're ending with. So if the top number is 11 here, what's the number here? 11. It stays the same because that's a 0. The bottom number is 6. If that's a 1, what must this number be? A 5. Awesome. Okay, so these have to equal the 6. So what element is it? Boron. Perfect. Okay, so that's what it's going to be decaying into.
For beta, you put you didn't put negative, you put 1.
Oh yeah, this one. Sorry, this one needs to be a positive, by the way. This up here. Oh, I'm sorry. Is that positron emission? Sorry, I lost my some of my lines. That's supposed to be a positive one. Sorry, they deleted a little bit. This is the negative one. Okay, thank you. Yep. Typically on beta minus, though, they don't show the minus up there anyway, but in beta plus they do. In the positron, they show the positive. So you can see, like on your periodic table, if you look back at the periodic table again, that's what they do on the periodic table, yes? So beta minus, oh, they do show the minus. They show the minus and the plus on the periodic table. But typically, if you just say beta, then that would be indicating beta minus. Gamma's the last one. These are usually accompanied by any of the processes above. Gamma particles have no mass and no charge, but they have a really high frequency. What's the danger of gamma? Remember we did run who? Run, Mark. It's Vicky, your ex-girlfriend. That's the fastest. It's got the highest frequency, which means that these particles are going to be so small they will actually pass through you. But guess what they do to you when they pass through you?
Kill yourself.
Okay, they starts with an M. They mutate your cells. Nice. And if that ends up taking over and you have too many mutated cells, it turns into what? Cancer. Okay. And so these are very penetrating. These are the most dangerous. X-rays come right before gamma rays. And when you go to get X-rays at the dentist's office, for example, what do you need to wear? Lead jacket. So guess what these can be stopped by also? Lead or layers of... Actually, they'll use concrete. They'll use layers of concrete. And so when there was like a danger of nuclear attacks and things like that, they would have these shelters that were basically underground, like layers of concrete that they would have too. So that's the gamma. Now the thing with gamma, for example, if we were to add gamma in here, we would just say plus gamma. Okay, now what is the mass of it? 0. What's the charge of it?
0.
0. So people will say, okay, but if it's 0 and 0, then why do I even have to show it? The thing is that this is the most dangerous of all of them. Okay, and so the gamma radiation it's huge. That's really big. But that which is like on the periodic table, it just says that it's accompanying every single one of those. Okay, so let's try this out. Symbol. Okay, alpha particle. So let's do this together. This is more like just problems now. And then I'll have, I don't know if anybody wants to come up that doesn't mind being in the video, but we'll try A together, and then I'll have different people come up to do A, B, C, and D, okay? So this part first, the alpha symbol. So remember, what does it look like? It kind of looks like what? Like that fish. Okay, the number on top is 4 and 2. Memorize it, okay? So the sooner that you memorize it, the easier. So it's like helium. What types of ions or particles? So this is basically like a helium nucleus. The speed of it, it's actually a tenth of the speed of light. It's a tenth of the speed of light. What can it be stopped by? Do you remember?
Paper.
Paper. Awesome. Can be stopped by paper. And the charge. If it has no electrons around it and it's just a helium nucleus, which means it just has 2 protons and 2 neutrons, what would the charge be? Positive 2. Perfect. So this would be a positive charge, or a positive 2 charge. Okay. Beta and then positron. We'll do beta on the left and positron on the right. The symbol for beta is B with a minus if you want. And so it's a 0, and then what's the charge of it on the bottom? -1. Positron, we said, is a beta plus 0 plus 1. Good. Okay, the speed of this is approaching. They say that it's approaching the speed of light. Let's see. Approaching the speed of light. It can be stopped by what?
Wood.
Wood. Perfect. And then the charge. So what would the charge of the beta minus be? Negative. And the positron would be? Positive. Perfect. Gamma. The symbol for gamma kind of looks like that Y a little bit. And the numbers are? 0, 0. So you could just write gamma, okay, because it's 0, 0. Guess what? Just like the Ron Markets, Vicky, your ex-girlfriend, radio microwaves, those are all electromagnetic radiation. Those are all at what speed?
Light.
Speed of light. Perfect. Okay, can be stopped by lead
Or lead.
or concrete. Awesome. And then the charge?
0.
Neutral. Perfect. 0 charge. Okay, so let's try 4 of these. All right. So we're going to get neon 24. So it's going to be written as Ne with a 24 on top. And then find neon on your periodic table. And what is the atomic number for neon? 10. Going through alpha and gamma. So what do I do? What do I write next? The arrow. The arrow comes next. Only a few people did this out of my 100 students that took the quiz last year. But there were people that put the alpha and the gamma on this side. It's decaying into that, so it's actually being given off. If you write it on this side, what ends up happening is your total comes out wrong. You're adding these on this side to equal 1 total. That's wrong. So it's decaying. Okay. So go ahead and try these. Should we do this one together, and then I'll have you try this?
Yeah.
Or go ahead and try this. Okay, go ahead and try this. So we'll pause for just a minute, and I'll have somebody come up and just. Okay. So Revere's going to show us how to work this one out too. So, all right, perfect. He's got an alpha particle, a gamma particle, and then he ended up with oxygen. You all agree? Yes? Okay, awesome. Okay. Herschel. Thanks, Revere. All right, Herschel's going to get the next one here for us too.
Yeah, Herschel.
Yeah.
0, and then since 0 here stays with 28 as the mass number, and then -1 here, which makes the 13 goes to 14. And 14 is silicon.
Do you agree?
Yeah.
Yes, very nice. Nice job, the
Yeah,
explanation.
Herschel.
Thank you. Okay, somebody. Awesome. Very nice. And people will ask, does it matter where the gamma is? Does it have to be in front of the platinum? No, it doesn't. Yeah, so that's great too. It doesn't matter. It can be on either side. So she's got the 188 and the 78 for the platinum. Awesome. Very nice. Good job. And nice. Do you want to explain it?
Yeah. It's these numbers minus these numbers. Here's the kicker. Equal these numbers.
Perfect. Awesome. Thank you. All right, good job.
It's like magic.
Okay, awesome. And that's the end of the nuclear radiation.